Okay, so in the second part of inverses, we're actually going to discuss the inverse of y equals mx plus b in a general form. So to find the inverse of y equals mx plus b, we got to do that trick where we switch the x and the y. So it's x equals my plus b. And then we want to solve for y again. So I'm going to move the b over, and I'm going to divide by m, so that y is equal to 1 over mx minus b over m. And this becomes the general formula for the inverse of a linear function. Okay? So this is not true for horizontal lines. This is not true for horizontal lines, obviously, because you have a y equals 0, so you have to consider that a little bit more deeply. And basically the inverse of any linear function will have a reciprocal slope right there. But it can't be true for horizontal lines because horizontal lines have 0 slope, and so you would end up with the inverse function being a vertical line or something maybe undefined. But this isn't true for horizontal lines because the horizontal lines have a 0 slope. And so this becomes a problem with reciprocals. So this is a reciprocal, which is 0 slope, no reciprocal. So that's why it's a problem with horizontal lines. But in general, when you want to find the inverse of y equals mx plus b, that would be your inverse function. So now consider some curve of f. Consider some curve of f and tangent line at AB. So we know that f prime of A is the slope of tan line at A, and that the second piece, so that's one, then the second piece of that is that y minus b equals f prime of A at x minus a. And 1 and 2 are true for f. What about f prime? If 1 and 2 are true for f, which is what we've already done, what about f prime? Well, we can use that idea of the reciprocal there then by saying for the inverse, y minus a, because you're switching the x and the y, right, equals 1 over f prime of a, x minus b. So notice that I switched the x and the y, a and b, and notice that we now have a reciprocal for the slope. So what this formula allows us to do is find tangent lines for inverses given f. Why would we care about this? Well, sometimes inverse functions can end up really nasty, or potentially they're really not easy to find, or some other number of things which would make working with the inverse function directly unfortunate. So if we're able to identify the function, and we're able to identify that the function indeed has an inverse, we can find the equation of a tangent line to model some very nice linear piece, for example. We can model that nice linear piece using our linearity and using this relationship between the inverse function and not. So this is the first formula that you'll need for your home fun. If you indeed know f prime of a, if you indeed know f prime of a, and you indeed know a and b, and you know that f has an inverse, you can use this formula to find the equation of a tangent line for an inverse by simply plugging in the a, which had been x, for the y, and the b, which had been y, and for the x. And instead of using f prime of a, you use 1 over f prime of a.